Hi, I'm Bob Alsop with ShopSabre CNC. Around here they call me RouterBob. We got a great video for you. You know, one of the neatest products I've ever seen made on a CNC router is a thing called a Lithophane. And you basically take a photograph and you create a surface based on that photograph, on the lights and the darks, and you machine it as a 3D surface. And it looks normal when you look at it. When you hold it up to the light, it's absolute magic. So that's what we're going to make. Now, there's something else that I wanted to kind of talk about in this video also, and that is, can you justify making things that are relatively, have long cycle times? And the answer is a lot of times you can. So I've actually selected a machine that you would typically make kitchen cabinets on, and I'm going to show you how you can set it up to make a Lithophane. We're going to be using Aspire to do this. Before we go in and look at the Aspire software, let's take a look at the features on this machine. The machine we're using today is the ShopSabre Pro series. This happens to be a 4x8, and it's absolutely one of my favorite machines to run. You know, people ask me all the time, how do you judge a machine tool? I said, well, it's really not that hard. I start at the base, because if you don't have a good base frame, nothing else you put on there matters. We use structural steel. It's an all-welded one-piece base, and that's really why you get such good edge finishes and such good accuracy. Now, the other part of the frame is actually the gantry itself, and we use a structural steel gantry also. And that's actually supported on the frame with these supports, and they're structural steel. So that's the most important components to creating a quality machine tool CNC router. Now, let's look at motion. You know, the next area I look at when I evaluate a CNC machine tool is actually the motion system, what makes it move. What we do at ShopSabre CNC is we start with precision ground contour guide rails. Those actually create the axis of movements, and then we actually use precision ball screws to create that movement. Now, let's talk about that a little bit. Sometimes we get a question, you know, are ball screws better than rack and pinion? Well, the answer is yes. They're more accurate, they don't have play in them. Now, one thing that's really funny, some people who only have rack and pinions will try to tell you how they're good, yet they use ball screws on the most accurate axis, the Z-axis, because it controls depth. We use ball screws because our design criteria is to create a machine tool grade CNC router, therefore we have to use ball screws. Now, what actually makes the ball screws move are motors, and we use closed loop servos, and they're Mitsubishi. So the Mitsubishi motors and drives are matched for this entire system. Now, the final component of motion control is the machine control itself, and let's go take a look at that. Okay, we developed the ShopSabre MMP controller based on some real rock solid control technology from Mitsubishi. And we did that because we wanted the reliability that Mitsubishi is known for. But there's another part of machine control that you have to consider, and that is the people part, or the user interface part. And our goal was to create something that was real easy to use and easy to learn, that a typical worker could master, that I didn't have to have someone with a technical or engineering background. And so one of our first goals was to accomplish that, so we put all the controls on a single screen. So everything the operator needs to run a machine control is right there. Now, that screen is actually running in a Windows computer. And we did that for a couple reasons. One is that allows us to network to the company network, and that lets us transfer files from the front office. So that was one reason. The other reason is nowadays it's real popular to actually run software on the machine control itself, and the Windows part of the system allows us to do that. So that worked out really, really well. Let me show you how you actually use this controller. All right, the first thing I do is I load a program. All right, it comes up, and then there's a little eye over here that I can click, and it actually draws the program. So over here on the graphic part of the screen, you can actually see what you're going to cut. So that's visual validation that you've loaded the correct program. All the buttons that you need to move it around are there. You simply hit cycle start, and everything works. So it's really created a great system so that you know, a typical operator can be successful. Now, let's take a look at actually how we cut. So let's look at the router spindle itself now. This machine actually has an HSD ATC spindle. ATC means automatic tool changer. This machine is actually equipped with a 5-position automatic tool changer. And we make these in a number of different horsepower selections depending on what your application is. Now, one of the things I always like to point out when we talk about these spindles, I moved the dust hose out of the way so that we could see it better. These stiffener plates, now there's an interesting story that goes with those. What we wanted to do was to get the maximum edge finish that we possibly could. And so we realized if you could extend that tool plate down, or the stiffness of it, it would be better. All right, so here's how we started this. We opened up the finite element analysis software, and that's engineering design software that we use to design everything at ShopSabre. All right, so we said, okay, what our challenge is to increase that stiffness. So we plugged some different scenarios into the software, and one popped up that it looked really, really good. So we made the parts, we actually tested the machine, and it tested out really well, so we knew we were onto something. Then we stepped back and we said, okay, can we achieve the same result and reduce mass? And that's why you see these cutouts on both sides, and it worked out really, really well. So it created a much, much better spindle mount, and that's why these machines are accurate, and that's why the edge finishes are so good. Now let's carry this further. One of the things you also see on these machines is we have axis travel that's higher than the gantry. So there's 12 inches under the gantry here of clearance, but I actually have 16 inches of travel. So I can actually machine on top of a piece if it fits under the gantry. A lot of machines don't do that. Now there's another thing, as you look up to the ball screw, you see a part called a balancing cylinder. Now here's what that does. First off, you have a ball screw drive, all right? All of this is mass, and because of gravity, it's weight. So what we have to do is we have to raise and lower all that mass. Well, it's real easy to lower it because gravity is your friend, but gravity is your enemy going the other way. So what we created was a balancing system to take that weight off. So there's no more pressure going up or down on the ball screw. Now here's what that does. First off, it makes the ball screw last a lot longer. But there's another part of machining that people don't understand, and that's when you get into 3D machining. 3D machining is cutting the surface and you're doing a lot of up and down and Z. Well, the speed is actually determined by the slowest axis. So you can have really rapid X and Y moves, but if you're real slow on the ball screw, your 3D machining is slow. So this whole system, using a balancing cylinder, enables us to really, really do 3D fast. So that was a tremendous benefit of our design project on this, and it worked out really, really well. Now, there's one other part of the machine that we haven't talked about, and that's the machine table, and let's take a look at that. Now let's take a look at the table on this machine. This is a vacuum table. The material is actually phenolic. We also offer other table options. One is a special treated MDF that's very, very popular, as well as an aluminum table. Now, what's funny is I look at the label and it says 408, and so I think, well, that must be a 4-foot wide machine. But when I put a tape measure on there, I get a little bit of a surprise. When I measure the table, it's 5 feet wide. And since we machine the table on the machine with the router, I know I have full table coverage. Well, the benefit of that is I can take a 4x8 machine and cut those 5-foot by 5-foot pieces of Baltic birch that you make drawers out of so often. So I don't have to buy a larger machine just to do that. Now, typically these machines would be used on nested base manufacturing, and you use a technology called flow-through, and basically we pull vacuum through an MDF panel, and that holds the parts. And the design of the vacuum system is really, really important, or the small parts move around on you. Let me tell you how we did it. If you notice, we start out with 8 vacuum ports, and they're large. Okay, they're rigid tube. We don't use flexible hoses because you lose some vacuum flow because of the interior of that. Those actually then feed into a vacuum plenum that's actually a frame member in the machine base frame itself. All right, we have 4 valves that control the zones, and then the plenum itself is connected to the back of the machine with a large 4-inch pipe. So you get tremendous flow on this design, and where that helps you is when you're doing nested base stuff, the small parts don't move as bad. So it's a really, really nice design, and it's been very well thought out of. Okay, now we've looked at the machine. Let's go look at the software portion of this demonstration. Well, I wanted to show you how to make a lithophane today because it's one of the neatest things I've ever seen in routing. Now, in case you don't know what that is, basically you take a photograph. We bring it into the software, and the software reads the highs and lows, and lights and darks, and it assigns heights to it. So it becomes a 3D surface. Okay, then so we adjust the total height of the 3D surface, and then we set it into the material so that just a little material is left for light to come through. Then it's a 3D operation, so we're going to use a tool that's got a ball nose on the end, and it's just going to go back and forth. And we're going to have a small step over, and it's going to take a little while to machine. But when you're done, it's absolute magic. You hold it up to the light and it's just magic. And it's a really, really great basis to make signs and all kinds of different things. Now, outwardly, you might say, well, that's fine, but that 3D stuff takes too long to make. Now, 3D stuff can also be some type of molding that you put on a cabinet. Well, I want to unpack that a little bit, because if you're saying I'm running my machine all the time and I have to stop doing cabinet jobs, for instance, to make that lithophane, I'd say you'd be correct. But in most cases, that's not the case. Most of the time, there's time during the day your machine's sitting over there. Maybe you're assembling the last job. Okay, well, how much does it cost for me to run that while the machine's sitting there idle? Well, what it really costs is a few pennies for electricity and about 5 minutes of my operator's time, because that's all it's going to take him to actually set up that operation. All right, now, what did the machine time really cost? Well, let's unpack that a little bit. Let's say if you take a machine tool grade American-made router like a ShopSabre, it's probably got a useful life of 20 years, and maybe even more than that, because technically anything that wears out is replaceable. But let's just say for easy numbers, let's say 20 years. Okay, let's say that I'm going to work 5 days a week, 8 hours a day, 50 weeks a year. Okay, I get 2 weeks of vacation for 20 years. Well, that's 40,000 hours is what that amounts to. All right, well, let's say that you buy a machine, and by the time you get it shipped in and to changing wiring and whatever, maybe you've put $50,000 in it. Well, if you run the numbers, if you divide 50,000 by 40,000, it's 125. So that hour of time machining really in truth costs you $1.25. So you can afford to do 3D stuff. Now, let's actually open up the software and let me show you how you make a lithophane. Okay, a lithophane starts with a photograph. All right, so we're going to start with a photograph. We're actually going to cut this in some solid surface material. Let's see how this is set up. First on the screen here you see the photograph, but let's look at the material itself. Okay, the blank is actually 10 inches wide by 8 inches. Okay, it's a 1/4 inch thick, and I'm touching off at the bottom of the material, and the reason is that the amount of material I leave at the bottom of the lithophane is critical, so I want to make sure that that's correct. The origin is going to be the center, and that's what you see right here. So that's how we set this up. Now, the next thing is how do we create a 3D model out of that photograph, and let's take a look at that. Okay, now we bring the photo into Aspire, and it creates a component out of it. Now, let's look at what that component actually consists of. So I'm going to double click on this. Okay, and let's see, an easy way to look at this is in 3D. Okay, so now what it's done is it's actually taken the heights, or the lights and darks, and assigned heights, and that's what you see here. And we've got a total height here. Let's slide this back and forth. You can see the benefit. Okay, see, that makes it higher. Now, if you notice also, this is reversed, and here's why. Think about how this works. We're going to have light behind it, okay? So parts of the photograph, for instance, eyebrows are going to be darker, then you know the thickness of the material has to be more in order to block some of the light. So that's why it's inverted. Now, there's a couple magic numbers involved in making a lithophane, and the first one is how thick is the total surface, and that's this number right here. They call it shape height. The number is between 0.1 inches and 0.11. So I'm going to pick the middle, so that's going to be 0.105. So that's the first number that we have to set. The other variable then is where does this surface fit inside the model itself, and so that's what we do next. So we'll close this. Okay, we're going to come over to the Toolpath tab, and we'll open it up, and we'll go to the material setup, and here's, once again, this carries over stuff that we set up, but here's something that you probably haven't seen. First off, there's my thickness of the model, and now watch what happens here. I can actually move that up and down the volume of material, okay? So this gray area here is actually 0.105, and then this is the thickness. Now here's what I want to do. The other secret number, magic number, is how thick this is, and the number is 40 thousandths, 0.04. All right, those are the two critical numbers. How thick is the surface itself, and how close is it to the bottom? All right, so we say OK. Now we're ready to Toolpath. Okay, the next part of this process is to actually apply the Toolpath. And first let's start with the tool. Because this is a 3D surface, we're going to use a fairly small ball nose tool, and it's actually a Vortex 2205, which is a 16th inch diameter. And we're going to use a very small step over, and of course the tool is going to go back and forth. So let's do that first. The operation will just be a 3D finishing operation. And this screen comes up, and here's where we select the tool. It gets to the tool catalog, and we pick the tool that we want. And all the feeds and speeds are set. All right, now if I want to change something, I can actually change that right here. You can see the step over is 10%. I could actually make changes. Those changes don't change the tool catalog. They only change this operation. Okay, the boundary is where we want to limit the tool pathing to be. In our case, we're going to use the model boundary. Okay, it's going to be raster, which means it's going to go back and forth. And let's just hit calculate and see what we get. Now, 3D toolpaths take a little while to calculate, so they have this nice little yellow bar that moves along at the bottom, and we should be almost done with it. And then we'll see the toolpath actually applied. All right. And there it is. Now, let's see what happens here. I'll turn that off and we'll just preview this. Now we're going to start out slow and then we'll speed the simulation up, but here's how it starts. It starts going back and forth. Now what that tool is doing is it's going back and forth, and then it's raising and lowering based on the surface. And when you get all the way across there, you have your lithophane. We'll speed this on up to get through there, and there's our lithophane. So that's the toolpath. Now, then we would output that, send it out to the machine, and cut it. Now there's one other thing that I want to talk about before we do that, and that's fixturing, because one of the things I wanted to do, we're actually going to use a Pro Series machine, so it's a big router. It's a typical machine you buy to make panel goods or casework or stuff like that. So what we're actually going to do is we're going to combine the vacuum table, the flow-through table, with a little simple fixture. Now lithophanes don't work very well with double stick tape, and here's why. Sometimes that material is real thin in areas, and you break it when you try to untape it. If you put tape on the perimeter, that leaves a little gap between the material at the bottom, whatever the thickness of the tape is. So what I really want to do is I want to clamp it down to a surface. So what you're going to see on the machine is a piece of material that's actually held down to the table with vacuum, and we can, because of our vacuum table design and the F4 vacuum system, we can isolate all that. So that's going to hold that down. Then we're going to have a couple of T-slots on there, and we're going to actually hold the stock down with clamps. Now the reason I did this is because I wanted to show you an easy way to do it on a machine that typically you'd use for nested base manufacturing that didn't take a lot of setup time. Okay, now let's go out to the machine and make this part. One of the things I wanted to show you in this video is how to make 3D parts, and we wanted to do a lithophane because it's really neat. But another thing I wanted to really show is how you do that on a machine that's set up to make cabinets or any other kind of case goods. And the way I did that was I took a piece of scrap material we had laying around, it's held to the table with vacuum, and then we attached some T-slots and some clamps, and now we're able to hold that part. So that's a real easy way to fixture things that doesn't interfere with your main nested base setup. Now let's take a look at this and see how it came out. It looks good from here. Now that's what it looks like. Now, it really doesn't look very good, but when you turn it up like this and look at the light, it's absolute magic. Wow, that came out great. You know, a Lithophane is a neat product, and it's something that you can really make on your CNC router. I had a great time doing this, and I hope you enjoyed it. If you need more information, you can contact us at ShopSabre.com. Thank you for watching.